Um, there we go. And yeah, as people turn up, we'll just, they'll be able to just sit in as we go. So first of all, thank you all for coming on this Friday afternoon and attending this virtual seminar. I'd like to start with, I'd like to start by showing my respects and acknowledging the people who are the traditional custodians of the land and elders past and present on which I am currently hosting the seminar, the Daruk and the Aurora people. And today I'd like to thank Associate Professor David Heslop for agreeing to present this seminar. Associate Professor David Heslop is a clinical academic at the School of Population Health at the University of New South Wales. His research focuses on cbRNE medicine, emerging diseases of pandemic potential and emergency response, using computational modelling and other simulation techniques to address previously inaccessible research questions. Today, he will be talking about integrating agent-based modelling and digital twins in environmental hazards and emergency response research. I'm very thankful, which all sounds incredibly interesting, and I'm very excited to hear this talk. I also encourage you all, if you do have questions, please send them through the chat. I will be gathering those questions because we will have a Q&A at the end of the talk. And from there, I will then ask those questions to David, and he'll be able to answer them for you. So I now hand over to David Heslop. Thanks very much.
Thanks very much, Nathan, for having me. Thank you, everyone, for being here over your lunch hour and work day. It's really nice to be able to talk to you about something which, as a researcher, there's quite a small community when it comes to this kind of work. So we have to look after each other is the first thing I'll say. So it's nice to know that there's people interested out there, which is great. It's also wonderful to have an acknowledgement of country, and I'll just add to the acknowledgement already that I'm talking on the lands of the Bedegal people, who are the traditional custodians of the land at which UNSW Kensington is based. So thank you for that. It's always a little bit embarrassing to have a spelling mistake on the title slide, so to apologise. We'll move on from that. But anyway, today, what I'm going to cover with you, just to orient you, is just a quick introduction to exactly what it is that I'm talking about in terms of digital twins, agent-based modelling, and how that fits potentially with broader systems modelling. And that really is introducing you to the topic of what's called hybrid modelling. It does have some other terminology I'll come to. I'm going to talk a little bit then about a project which brings together these concepts as an exemplar. And I'd like to share with you some of my, I guess, the limitations of the approach, some of the challenges that I've found using the approach, and some of the obvious problems, which I'm sure you may have questions about and how they could be solved. But all in all, an emerging area of new research that has been trickling through some of the more well-resourced laboratories and institutes around the world for some time in bespoke areas, and I'll touch on that in a second. But I think is now becoming more mainstreamed as software solutions become more available to researchers, and expertise is building within the and the numbers of modelers are increasing. So just to talk about that cryptic comment I said about sort of this is being used, this approach, before and for quite some time, as is typical of a lot of new emerging techniques, the first places to use these new emerging techniques like agent-based modelling coupled with environmental systems modelling have occurred actually behind classified walls in military research. And in very select areas. So military research focuses on particular areas. So some areas where agent-based modelling has been used at a very large scale, and we're talking potentially billions of agents simultaneously working in parallel within a synthetic environment, has been nuclear weapons research that's been going on at least since the mid-1990s on computing resources that are just inaccessible to the average person, of course. And similar research recently has emerged into climate change research, particularly where it has an economic intersection, which has been funded by government. So you will be familiar with, or may have heard of, a number of large projects being funded by institutes such as the Defence Advanced Research Projects or DARPA in the US, Lawrence Livermore, Argonne National Laboratory, and also competitors in Europe, China, Russia, and elsewhere, and in Australia. And so probably the most significant research group currently in Australia looking at agent-based modelling at a large scale would be Mikhail Propenko's complex systems laboratory at University of Sydney, but its focus has been not in environmental modelling so far, which is understandable. COVID has come and there are a few other focus areas they work on, but my work aspires to and works in similar domains as their laboratory. So what is this hybrid modelling? So we hear about what agent-based modelling, and I'll talk about what a software agent is and how it's important. But agent-based modelling has its limitations. Firstly, terminology. Agent-based modelling is sometimes called individual-based modelling. Agents are sometimes called software agents. But the concept is the most important aspect of what an agent-based something is, or individual-based. And that concept is essentially an autonomously operating logical process, or generalized logical process, GLP, which can be defined in various ways internally to that object, working in a synthetic environment where there's a number of different key factors occurring, and or features occurring, and that is there's data, there's processes, or the generalized logic of using that data, and communication. So the coupling of autonomy and those three things together, those three things together essentially is otherwise more recently known as a digital twin. So we'll come back to how they're very similar, or if not the same. But the coupling of those two things together is incredibly powerful. The problem has always been computational techniques and software to actually achieve a model which is meaningful. To quote a very well-known phrase, of course, all models are wrong, but some are nevertheless useful, and that's very true. So there is a level of abstraction or simplification, in other words, that one imposes as the modeler as part of the process of generating these synthetic systems and agents that is imposed in order to use those models in a reasonable way, in a reasonable time frame, to generate an answer that's useful. So one thing that agent-based modeling is not, it is not a 100% faithful representation of a physical object. It is an abstracted representation of a physical object with a sufficiency of information or data and processes and communication algorithms and functions contained within. So hybrid modeling is more than agent-based modeling. It is a combination of taking an agent-based system generally as a foundation and using tools such as system dynamics modeling and discrete event modeling or process modeling in parallel to generate what's called a hybrid model. So that can be a system dynamics model contained within an agent. It can be a system dynamics model sitting outside of an agent-based system but interacting with it. It can be a process model inside an agent, a process model governing a population of agents, or many combinations therein. And therein lies this diversity that is suddenly exposed through hybrid modeling software and systems capabilities, that where you can have literally a suite of options at your fingertips. It's like a laboratory with different experimental techniques, and the process of modeling becomes essentially an extension of how much how inspired you can be as a researcher in both generating a synthetic environment to experiment within, but also how to answer research questions using the tools available to you. And that's why I found agent-based modeling so exciting and hybrid modeling so exciting, because it's such a powerful and diverse tool for answering questions in many different ways and approaches. So what does this mean in more detail? Sort of taking it down to a little bit, drilling down one level. You see here system dynamics, which is some typical annotation here. You can see on the top left is generally talking about stocks and flows. So essentially what that is in practice are partial differential equations being solved that represent flows between compartments. And they are solved using various techniques such as Euler integration or Rutger-Kutter integration to approximate flows over time in a system of linear differential equations, essentially. So that is system dynamics modeling. It's been around for now 70 years or so. Process-centric modeling is discrete event, and that means we're talking about how individual binary agents, as in an object, move within a process diagram represented as a graph. And so that is not a continuous representation of data. That is a unitary representation of data, and is useful for looking at different things, such as how an individual agent may choose between different pathways in terms of a decision-making process. So things such as manufacturing processes, supply chains, and other economic models often get pushed into process modeling or discrete event modeling. Agent-based modeling is the thing that is the glue almost that sticks it together when you do hybrid modeling. So I tend to see process-centric discrete event modeling, system dynamics modeling as being complementary to a foundation of agent-based modeling, which emerged much more recently in terms of tools that can be practically used by the general researcher. So the one tool which I use, which I find very useful, and you get often familiar with those tools, is AnyLogic, which is really it's a commercial product, but and there is an open source version called Repast, R-E-P-A-S-T, Repast Symphony, which is essentially the open source version of AnyLogic, and those two are written in Java. They are very powerful, and they support full hybrid integration of these three methodologies. Many of the other technologies available for agent-based modeling do not have the ability to integrate properly these three methodologies, whereas AnyLogic is probably the only one on the market that can do that at this point in time. And so it's an incredibly useful tool. I'm not going to promote AnyLogic any further in this talk, but just to say it's worth a look. You can download a personal learning edition and have a play. It's quite an interesting piece of software. So just to touch on this agent-based, what is it? In a simple sense, it is the ability to define autonomously acting digital twins, essentially, or autonomous agents working in a population in an environment. So when you define an agent-based model, there are a number of different things that you're looking at. You're looking at what happens within each agent. So you have different types of agents, and you start to define how they operate in different ways and how they interact with each other. And you define an environment in which it acts. And so that environment in which it acts is the most important other part of the agent-based model, and how each of those agents interact in a way which is valid is determined by a thing called the modeling engine. And the modeling engine underlying an agent-based system specifically addresses the issue of bias in relation to computation as it relates to modern computing systems. The best way to think about it is this. Most of you will not be aware of the fact that on a single core or a single processor, only one process can happen at any one time. When we use modern computing systems, there is multiple things happening simultaneously, but it's a trick, essentially. So either you have multiple cores, or you have a thing called multi-threading. But in each case, the actual processor gets used sequentially by each one. And it's how that's divvied up, that processor time in what order, that is most important. Agent-based modeling is conceptually different to how most software runs. What you're looking for is independent autonomous agents essentially operating in parallel. So unless you devise a computer system where each agent has its own computer core, and that computer core can run essentially like an independent processor, but only for that agent, which is not currently achievable, then you are essentially having to emulate a parallel processing system, which is what the agent-based modeling systems do. So it's very important. There are some recent really exciting developments where graphical processing units, or GPUs, can now be used to run in parallel millions of agents simultaneously, whilst a CPU operating in parallel runs other parts of the modeling system. This is going to super turbocharge essentially large-scale agent-based modeling. But one of the key things about agent-based modeling is that there are some limitations on processing power. So quickly, I'm going to very quickly skip through this. What's an agent? Well, this is you would recognize this, the Globe Theatre, where Shakespearean plays are done. And so an agent environment is essentially, what you need to do is say, this is the environment that I'm going to allow my computational agents to operate within. It has characteristics, it has certain states associated with it, like temperature, volume, physicochemical characteristics. It might change over time, it might evolve, and so on. And then we're going to introduce into that environment agents that contain states, behaviors, interactions, their own characteristics and own states, and memory and other functions and communication. And so these agents, as I mentioned, are autonomous decision-making entities that work in parallel in an emulated environment. And so they vary by their characteristics or by available accumulated resources or interactions with the environment. And from a conceptual conceptual way, essentially, they have memory, autonomy, effector organs, sense organs, and it starts to sound very similar to the definition of what a cognitive agent is. But most agents, for the purpose of modeling, particularly environmental modeling and for emergency response modeling, we don't want them to be cognitive agents. We want them to be abstract agents that do a sufficient amount of simulation to produce an answer to a research question that we're interested in. We don't necessarily want artificially intelligent agents running around our computers' memory. So some examples of agent systems and approaches that have been done in the past are summarized in this slide. This is from Grigoriev, who's part of the AnyLogic group. You can model people individually, in groups, in populations. You can model non-material things, investments, products, agreements, contracts, equipment, transport, organizations, opinion, and then more abstract concepts like trade and so on and so forth. They're actually relatively easy. And so many of these little glyphs here and icons indicate organizations that we know have used agent-based modeling extensively to answer questions on their behalf. But what environment is valid? And so it's interesting to talk about this. We talk about environmental modeling, and we very much immediately think, of course, of GIS modeling, but there are other, I guess, best way to think of it, abstracted environments in which humans operate that can be conceptualized as environments. And so there's a networked environment, like a social network environment, which can be relevant, a human interpersonal contact environment for example, epidemic modeling. We might be not particularly interested in where the contact had occurred, but the fact that it did occur and occurred to this household, which has got little, like a network model. And then in many cases, we want to simplify it well down to, for purposes of control of variation within experiments, to either a grid, which is like a von Neumann neighborhood, or Euclidean space, either 2D or 3D less commonly. So agents fit within our globe theatre. These are not typical Shakespearean agents, but this is what happens. And we, look for what happens under certain rules. And one of the key things about autonomously operating agents is that combination of simple rules can actually produce quite complex behavior. You may be already familiar with cellular automata, like von Neumann automata. There are famous examples like Conway's Game of Life or Gosper's Glide Gun here, which just show how very simple rules in terms of how each individual block reacts to the state of surrounding blocks or grid zones within these two examples here, that can produce what appear to be epiphenomenon which look organized, which is quite interesting. Now, whether those epiphenomenon actually have meaning is something which depends entirely on the system, but essentially you can have unexpected or unintended outcomes from these otherwise, for want of a better word, complex systems that can emerge. And the advantage of agent-based modeling is that you can explore this space in terms of the complexity of systems and how they operate, and that's important. So modern agent-based modeling really relies on a number of new software systems. I've touched on the issue of parallelism, which is emulated within modern systems, AnyLogic really being at the lead. It's got the majority of the market, but other ones that you may have heard of are Jade, Mason, NetLogo. If you've heard of these platforms before, there's a review that you can have a look at from an epidemic perspective. There are a number of other reviews out there available in a number of journals. I'm happy to provide those references if required. So the next step is, for a new technology, how to define it. I'll very quickly go through this to say there are now standards about how to actually design these things. It's not a creative exercise completely. There is some rigor associated with it, and it's associated with understanding how to define the autonomous and communication aspects of each of these agents. So the ODD protocol by Grimm and Railsback has now been really extended into a cognitive approach as well in a second paper. These are some of the design concepts which are particularly interesting within that design approach, such as emergence. And a good example of emergence being the shapes of starlings as they move in 3 dimensions in migration, which is called murmuration because of the sound it makes. As this occurs, you can look it up on YouTube. But it's a fascinating example of an organized entity or epiphenomenon due to a complex autonomously operating agents where only a few decisions are being made. And I believe there's a paper that's been published which actually boils down the key decisions that each starling makes independently, but in the same way, each of them to produce this particular effect. I believe it's 7 factors from memory. And there are other important things that get defined in the protocol, such as sensing, interaction, how stochasticity is important, and that is the statistical distribution of choosing different parameters, and various other factors such as learning, which can be or not incorporated into an agent depending on the research question, its response to stimuli in terms of adaptation, goals, and cognition, and other factors. So I won't go into great detail on this, but essentially to show that, to say that it's important when you're agent-based modeling to have a clear purpose, and that's tied to a research question. Again, it's not simply a programming or creative activity. You then define the key aspects of what the agent is doing and why it's important. And then you touch on these key factors, which I think are the most important: emergence, and some of the important patterns that can emerge are oscillation, gradients, waves, cascades, flocking. And these are related to, from a mathematical perspective, at the most simplest level, some of you may be familiar with the logistic map, which is a good example of how order can then degenerate into essentially chaos as a natural consequence of the mathematical relationship mentioned here. And this is typical. We typically see this in natural systems. There is some excellent research which shows how natural order can degenerate as per a bifurcation graph like this in simple examples of binary decision making in the natural world. A fascinating part of what seems to be natural, a natural interaction, an emergence of certain mathematical principles. So something again that I can come back to and pass on some papers later. What I'd like to do is move on quickly to the project that I've been working on. So I've given you a background of, what is this new technologies that's out there, and you might be thinking, how on earth could this be used in a research setting? I hope to bring it back to ground a little bit and ground it into an example. Chimera evolution, and there's nothing special in the name, is a conceptual software development project that I've been working with the Department of Defence for some time. It is focused on answering questions relating to the potential exposure of personnel in dangerous environments, and those environments are generally in the context of operations, and the kind of dangerous environments relate to the potential for exposure to biological and chemical hazards of the most dangerous varieties, such as chemical weapons or biological weapons, or highly transmissible agents. And the purpose of doing this research is to offer essentially a platform for answering questions about how you might approach a particular task, or what kind of risk controls you might want to put in place and give an estimate of the kind of impact that those risk controls might accord for what otherwise would be potentially catastrophic outcomes. So it is partly a large-scale agent-based modelling system. It takes inputs from a wide variety of data sets, but it, in essence, integrates those into a piece of software that is based on any logic that allows you to have a look at the interaction between an environment hazard and an agent, and then the impacts and interactions between each in a geospatial environment. Essentially, as I mentioned, it is designed to be a prototype which can be developed in the future into something which is more of a product for consumption within defence or outside of defence. And essentially it allows an end user to design a particular scenario and then insert into that different modelling components, either geospatial or particular populations of agents in a particular hazard context or scenario. And I'll give you an example of these later. A key component, and I'm going to focus on this today, is the environment model. So if you'll bear with me to explain the environment model, and then I'll show you how it integrates, and then we'll be finished. So I selected a particular type of model based on some of the problems that we've confronted previously in environmental modelling using purely plume modelling, which is commonly used, or atmospheric plume modelling, I should say, in where the actions of individual agents on hazard are not accounted for, and how things progress over time in terms of decision making are not easily explored. So the environment model that I chose to use in Chimera evolution is a compartmental fugacity-driven environmental fate model, which is fugacity models were pioneered by Mackay and McLeod. Some of you may be familiar with this. Extended by Miriam Diamond is sort of the particular bespoke version, or I guess the extension which I was most interested in was the work of Miriam Diamond. She's over at the University of Toronto and has looked at how urban environments can be coupled with fugacity modelling to give you answers about where hazard actually accumulates, deposits, and undergoes various other processes over time. In the Chimera model, it's a 2D cellular model, so it's not three-dimensional. and it overlays and interacts with agents working in a continuous GIS space. The model is solved in real time using model execution, and it's coupled with a Crank-Nicholson-driven dispersion model, which allows you to look at how advection and advection only and a little bit of dispersion works over time within an environment, a defined environment. So under the airflow characteristics, a vector field, for want of a better word, of airflow, where dispersion and advection will move the agent over time. Parameters in terms of physicochemical properties have been drawn from published sources and adjustable estimates or surrogates, depending on whether that data is actually accessible or not. And so surrogates meaning if a hazard, if a parameter relevant to a particular hazard is not there, then we would generally default back to a close relative in terms of the chemical class or biological agent, physicochemical characteristics. This may again be a little bit dense, but just to say the way that a fugacity-driven model works is that if you, and I'll show you some diagrams which will be helpful and shortly, but essentially you need to have a mass balance. You inject into that or use various basic physicochemical parameters for a hazard. And here I've got two chemical agents, sarin, an organophosphate nerve agent, and a which is predominantly which has a essentially it is quite volatile, and it will be mainly dispersed through the air compartment, and distilled mustard, which is less volatile and will generally be persistent within the environment more under normal conditions. Coupled with this are things called Z values and D values, and this is not a lecture on fugacity modeling, but essentially these define how the transitions between different physical states within the particular compartment or zone we're talking about in the geospatial model, how those particular processes work mathematically. So diffusion from air to water, rain from the air compartment to a water compartment, like a still lake, for example, or a pool or a pond, wet deposition, dry deposition, air to soil, air to film, film being an abstracted compartment representing a surface film over objects within the environment. And then in addition to that, reaction and advection, I've already discussed, being handled by a Crank-Nicholson equation separately. So if we look at a general conceptual model of how this model works, you have a source of a hazard that can, say, for example, for argument's sake, is dispersed into the air or onto the ground surface at the same time. You can have transport from the air to another air zone nearby, so horizontally across the environment. It can react by degrading or transformation, and that air can exchange with the ground surface. So you can have air deposition onto the ground. You can have ground resuspension into the air. That's governed by certain processes which are mathematically defined and have been over many years validated under various conditions, which are available as references, which is useful. Ground surface, and on the right-hand side, we have humans here, or objects. So humans can be contaminated, they can inhale or exhale, and they can have the presence of a respirator or other risk control. And then on humans, humans again can transport contamination themselves through to various other zones and deposit that. The hazard within the human can degrade, and the human can has a certain capacity to absorb. So one of the key points about fugacity defined as pressure, fugacity defines the ability of a compartment within an environmental zone you're modeling to essentially hold what holding capacity does it have or what avidity does it have for that particular hazard. So some hazards like PCBs or organophosphate chemicals or fertilizers, for example, have a predilection for lipid phases of animals, and they may bioaccumulate within those biota within the environment. Equally, there are some which have an avidity for soil, and so they may over time accumulate in the ground. And some may be more avid for the air and will not really accumulate within the ground surface, in the ground or in biota. So this modeling technique allows you to look at different. It generalizes the problem of how hazard actually disposes within an environment. But the key message is there is a total mass balance, which allows you to generate what I showed before, which is mass balance equations, which can be solved using various techniques. All right, so just to show you some examples of results from validation studies within the model. In this particular example, an indicative mole of sarin, which is an organophosphate nerve agent, was deposited into a 100 by 100 grid here. You can see in four compartments. So essentially these are stacked on top of each other as virtual potential compartments for which a hazard could dispose into at 0 time through to 480 minutes. And so you can see here that, and just to highlight, the each of the color scales is standardized for each different compartment. So what looks intense in the film compartment actually represents, it's simply for visualization purposes, actually represents a very small fraction. Otherwise you would see actually almost no hazard at 480 minutes. In film, if I standardized all of the numbers across all the different compartments. So I'll explain more as I go on. Essentially, at the bottom right here is release into the air compartment. In the top left is a simultaneous release into the soil compartment. And then you run the model and see what happens over time. And what you see is redistribution within each of those compartments, because there's no advection going on, there's no air movement. You see redistribution over time into the soil from the air. So at the bottom right, the soil gradually accumulates from the air. From the air will accumulate some from the soil in reverse through re-aerosolization or off-gassing. And the water compartment, which is within the same zone, an element of water, which is modeled, essentially from both compartments will gradually accumulate. The film compartment, again, will gradually accumulate. And the difference is, you can see on the left here, graphical representation, the diamonds, circles, and triangles, so the upwards pointing triangles on the left-hand axis in moles, and the squares and downward facing triangles on the right y-axis in moles, but a small fraction. And you can see that the mass balance is maintained, which is the total, which is what the point, which is a precondition of the computational model. But you can see redistribution over time with an equal amount distributed initially between the air and the soil compartments, then gradually over time moving into the water compartment and out of the soil compartment, and from the air, sort of into the air and then out of the soil. So you can see here that sarin would from want of a better word, prefers or has an avidity for being in the air, which is what we expect from sarin based on its solubility and volatility. But there is a small amount which gradually accumulates over time on film or in water, which again is what we'd expect from sarin. So this was helpful to know that the model was, in terms of Chimera, was operating as we intended. Subsequent validation, we looked at sarin with some advection. So this is showing a uniform velocity field moving from the bottom left to the top right. What you see here is the same release, just a little bit repositioned, and then over time it gradually moves, and you can see how the masses distributed in accordance with advection as well within that, using a Crank-Nicholson driven model. And then mustard, which is a highly persistent agent, has a slightly different pattern, where there's much less avidity into the from moving from the air, from the soil to the air, and from the air to the soil. And that might be surprising for a persistent agent, but it actually mustard is not as persistent as you might think at normal temperature, but it essentially shows how the different physicochemical characteristics of the hazard influence how it distributes across different compartments. So how do we integrate this all together? So I've shown you the environmental model. You're all environmental modelers, I think. So I wanted to focus on that, but in the interest of time, I'll quickly step through this. We want to bring that kind of model into an agent-based model. So bring in the dispersion, which is Crank-Nicolson driven in this case, and fugacity models together into an integrated model and start answering questions. So what we did is we defined an environment where there is essentially zones that can be defined within a geospatial environment and model these independently using a dispersion model, and have agents essentially interacting with those hazards either in the air, the soil, on film, and being contaminated and depositing, and essentially we're counting for where hazardous material goes within the environment. And so that was done, sorry, complex diagram, but essentially by constructing a multi-layered integrated model, the layer one being understanding how the environment model interacts with agents through things like exposure models, a risk management model, and a hazard distribution model, which I've just shown you. And then that interacts with a conceptual layer, which essentially defines the impact of that interaction on hazards, on agents. And that involves physiological effects, clinical indicators, how, if the person's going to end up being a death in a week, or in an hour, in a minute, whether somebody needs medical attention, and how that then interacts with, on the right here, a layer three, which is a decision layer, at the moment quite rudimentary, but essentially does this impact on how these agents are performing or deciding or behaving within this synthetic environment. And so this is quite typical of an integrated agent system where you have this multi-layered interaction between environment and decision-making autonomy, essentially. This is all underpinned with a whole range of basically database-driven model parameters that can be accessed by the system as required. I'll skip over this. How things actually work is that we might have different areas within the environment that are essentially operating at any one time, and other areas that are essentially quiescent during the modeling run. And these allow the model to run a little bit quicker. It's a bit of an optimization approach. And so we may have various events such as exposure events occurring within particular areas that leads to outcomes, which then get gradually data is collected from those in terms of outcomes, and that leads to events within populations that we're interested in terms of avoiding certain outcomes or documenting certain outcomes. So to bring together how it all sort of fits together, the agents and the environment model, we have an object or a human which essentially can be contaminated, can breathe in and breathe out, can touch. There are objects that can interact with it, and hazard can move between those objects and humans through direct contamination, or you can essentially be exposed through inhalation with the risk control or not. This then works within an environment model where diffusion can occur within zones and between zones slowly, but more commonly advection occurs, which accounts for horizontal movement. Within a particular zone here on the right, you have essentially the multiple environment models, which are fugacity driven, which are being driven by all of those processes that I mentioned before, and allow you to work out where hazard's going to be. So, for example, you may have 100 humans coming into a modeled environment. Hazard may have been released an hour ago, but by the time that the agents actually get into the environment itself, either it's redistributed within those zones into a state which is not particularly hazardous, And there's no contamination to occur, and so essentially it may not be relevant, or advection has occurred and it's not there anymore, and what's remaining is actually essentially sequestered into the environment in the compartment. So this accounts much more for accounts for a lot of the effects that we see in highly dangerous hazards that work like chemical hazards in the environment, where the plume model doesn't really match what we see on the ground due to these kind of processes occurring, like rain and deposition and other factors. Equally, assumptions like re-aerosolization, which is incredibly dangerous for certain particulates, for example, from surfaces, can also be accounted for in this way. And so one of the key things about Chimera is we're quite interested in this concept, or I'm quite interested in the concept of evolution, which is why Chimera is called out Chimera evolution, the evolution of hazard over time. So the effect of things like exposure to environmental radiation, like UV radiation, on biological hazards. What does that mean? Are we going to see an activation over time? Impacts of things like heat over time on chemical agents, and other factors. Again, difficult to model, but I think for me, an important step forward that I wanted to move with the modeling approach that I've taken. What does it look like? Essentially, there's a scenario editor. You can generate this is Holsworthy Barracks. You can generate models that can be constructed into that environment using markup for various components of a base, for example, or a military environment. And that essentially gives you the ability to generate essentially a scenario definition, which has got a whole range of factors. Just as an exemplar, this just shows very simple early work, but essentially you can have a plume model, which is then running over the top of the GIS model, which is interacting both with the agents which would be present in that environment, but also redistributing itself within that environment. So you can visualize the air compartment, the water compartment, if water is present in that grid zone, the soil compartment, or the film compartment, up to you. And this is just an example of sort of some of the how you can place objects within that environment, and then you collect data from those individual agents. This is a whole series of agents in barracks in a particular zone, and these can be used again to collect data, to look at individual outcomes, and on top of that, you can populate those agents as part of a human population which has got factors associated with it, such as age, vulnerabilities, medical factors, and so on. And this is an example how the Crank-Nicholson plume, it's not a particularly great representation of the concentration. I apologize for that, but it just shows how movement over time under wind conditions works using the Crank-Nicholson advection model and dispersion model. So something of interest for you. So in the future, we want to extend this into larger scale multi-agent systems. Multi-agent systems require very powerful computers, multi-core systems, and essentially addressing the issue of parallelism and synchronization. So you have to compartmentalize or cut up the model into bits and run it in parallel. The only way you can do that is to synchronize each of those cut up bits in time, which is hard work. More complex scenarios, which is easier because we've already got the system done. Extending the hazard database beyond what we've done, which is a few hazards so far. Complex agent decision making, again, this is taking this more into the anthropological world and collecting data about how people behave in certain situations and seeing the effect of that, and incorporating, and this is of particular note, the major limitation being I do not like the dispersion model that I'm using. It's expedient, but I would prefer to use something like Cowpuff or another validated dispersion model for future work. So essentially, that leads to this concept of standardization of digital twins, like humans model humans in digital environments, which is a potential future direction that we'll be taking. And I will then open up to questions. And I'm sorry, I ran a little bit over time, Nathan.
That's all okay, David. Thank you very much for that. That was super interesting. Love to open the floor up for any questions for David. I have a couple if people don't, but yeah, just unmute yourself and ask away. All right, well, I'll ask one. So I'm curious, David. Obviously, when you were mentioning about validating the models by testing out how certain contaminants work in the environment, how long does it take to generate something like that? Because I imagine that with limited computational sources and time, those things can take a while to determine. Like, how do you determine what validation process and how long you have to kind of conduct them?
Yeah, so the model actually runs almost in real time that we've got. So the thing about agent-based modeling is, for example, some of you will be familiar with computational fluid dynamics, and to solve a particular area, for example, takes hours at that level of detail. We, in collaboration with Defence Science, they were more interested in an approximate solution that was precautionary. So the validation step in terms of, and this was the subject of quite a lot of discussion. The problem is a lot of the potential interactions we're looking at have not been seen in, or there are approximates that we can look to for validation that are similar, but they're not exactly the kind of exact context we're looking at. So the best validation from the environment model is really comparing it to a model that has been validated in the real environment, which is something like CalPUF. We're working towards ensuring, essentially, we're working towards that, and it looks like it is reasonably valid. In terms of the fugacity model, that has undergone fairly rigorous existing validation in previous studies from other researchers. So I'm more confident in terms of validation of the fugacity model that it operates as we would expect it to do based on parameters and accepted models through agencies such as the US EPA, for example, who use the same kind of modeling to estimate how hazards disperse within compartments.
Okay, very cool. Jeff, I see that you're unmuted. Do you have a question?
I'm not sure. I'm trying to formulate a question. It was a fantastic presentation. Thanks, David. And it's really exciting, the developments that you describe. I suppose the challenge I have is more sort of pragmatic application to the current knowledge.
Yep.
And what you've described about, say, the modeling around exposure. So we do a lot of work to model exposure. And so we've got some familiarity with what you're talking about around exposure. But then the sort of stock standard EPI approach of doing, regression-based modeling to get associations and in terms of observational epidemiology. That's what happens there. And the challenge I have is to see how this links with what we do now, rather than the exciting connections of what we can do in the future.
Yeah, I understand what you're saying, and you're right. So one of the regression models, I think, are very helpful, and by definition, they work within a contained, controlled context. How that works in a simulated, broader context has to be very carefully done. So when I talk about abstraction earlier on in the talk, that process of abstraction is incredibly important, I think, to address that issue of taking that steps. If you create an environment where a computational or an agent-based model, or even a large-scale agent-based model in particular, which has essentially you're just making stuff up and saying, I think it works like this, and we're just going to run it and see what happens. And isn't that interesting? I wonder if there's no linkage to reality. So when I say abstraction, I mean it has to be deliberate abstraction, which is essentially taking a number or one step beyond exactly what you say, exposure studies, which say if exposure occurs to this, this is what occurs. So there's only so much I think you can validly do with these kind of large-scale models as first steps. It's not something you can, it's not like a computer simulation, like a game where you just sort of allow it to just run and say, isn't that interesting? What does it mean? It doesn't mean anything. So I just wanted to validate what you're saying. I agree with what you're saying. It doesn't take anything away from that epidemiology. In fact, that epidemiology is absolutely required to parameterize this kind of model. And when you run the model and generate the data, I think the caveat that goes with it is, this is under these assumptions, using this approach, this is what may occur, and then further validation is required using other techniques. Can we find examples in the environment, for example, of those circumstances that generate these unexpected results? So it's about using it to identify conditions which are potentially we need to validate. I think unexpected doesn't mean it's true. It means that we have to go and investigate. That would be my response.
And the other question is, do these work for chronic exposures? Like, this is where it's subtle exposures over long time periods, which is generally the case with a lot of environmental exposures.
So actually, yes. So I have taken this into the sort of the more short term. Actually, most of the research that's been done in this area has been longer term exposures, such as various chemical exposures in the environment, persistent chemical exposures within the environment. Some great examples from Miriam Diamond, for example, of water table contamination in Toronto and the surrounding Great Lakes as good examples of that. So yes, and can they be coupled with agent-based models? Absolutely yes. I see, actually, another way to put it, I see these integrated models as simply extensions of almost the existing approach taken through analysis, looking at pattern of life analysis, which is already done. So, what is the daily ingestion of soil by the average toddler, for example, is a perfect parameter to actually include within an agent-based model. It just allows you to take that data and start to work with a geospatial environment to start to look at the influence of aggregation in space and over time, to give you to extend it beyond just making an assumption to say people do the same thing every day for 100 days, or which I know that environment is done in environmental risk assessment, for example, under certain conditions. So yeah.
Right. Thanks very much for that.
Do we have one last question for David before we wrap up? Oh, here we go. Matthew James has just sent through a question. So for you, David, would a practical application be to use this modelling to assist in disaster waste management, for example, asbestos decision-making during large disasters such as the recent bushfires, or for assisting fast recovery and rebuild? I don't know if I've actually worded that question very well, but
if I've read it in the show, Nathan, that's fine. I think this kind of technique could be used. Essentially, as I said, it is an extension of using existing techniques, applying them into an integrated modelling system. Essentially, yes, you could, and that could. One of the biggest advantages of agent-based models is that you can run Monte Carlo simulations really easily. You can run 1,000 simulations and then look at essentially the risk of certain things occurring. So and using geospatial dimensions as well. So yeah. Look, the answer is yes. Thanks everyone for your messages as well. Appreciate it. Nice to see you all.
Cool. Thanks very much, David. And thanks everyone for attending the seminar. Yeah, it was a really, really interesting talk, and yeah, we'll have the seminar recorded and up available in the card Dropbox as well. So thanks again for your time, David. And thanks everyone else for attending as well. Much appreciated.
I really appreciate being here, and it's nice to have colleagues that I can talk to. Okay. See you.
Thank you very much, David.
Bye. See you.